Today we start with vector Okay. A vector field is something that has vectors placed in each point in space. Now, when would you need something like that? Well, in fluid dynamics, if you have some kind of water flowing, and if you have a steady flow, then at each point you have some kind of a vector, right? When it narrows, the velocity will be faster. When it's wider, the velocity will be slower. And because velocity is a vector, that means if you have a steady flow, you have vectors at each point in this space. So that's one example. Another example of a vector field is, say if you have a single positive charge, and because of that you have electric fields, right? An electric field at each point is a vector. So electric field, magnetic field, these things that we call fields in physics, those are examples of vector fields. Now, for us, we're not going to be worried too much about applications. We're just going to study vector fields as purely mathematical, but occasionally I'm going to throw in some physics in there to give you some context, because I want to give you some valid reason why we would want such a thing. Okay? But for us, a vector field is simply a function that gives you back a vector when you plug in a position. So if I plug in the location, I should be getting back a vector. So that will be a two-dimensional vector field. Here you have u and v, and these are individually functions of x and y. So as an example, let me show you an example. You could have something like this. So I just came up with two functions of x, y. This is a function of x and y. This is a function of x and y. I just place them together. And of course, this is a vector field because I plug in some number for each one of them. If I plug in a position, so let's say I want to know for this given vector field, what's the vector at the location -1, 2. How would you do that? Well, it means that any x has to be replaced by -1 and any y should be replaced by 2. So this x is replaced by -1. That y is replaced by 2. Here's an x, put -1 there. There's a y, replaced by 2. There's a -1. And if you compute this, what's that? 6 minus 5, -10, -12. So 5, -12 is the vector at the location -1, 2. So that's a mathematical example of a vector field, which is very easy to understand. You plug in two numbers, it gives you back two numbers. That's a two-dimensional vector field. Now, what's an example of a three-dimensional vector field? Just a three-dimensional vector field will give you three numbers, right? And u, v, w will individually be functions of x, y, and z. By the way, in here, u is x plus 3y and v is 5xy plus 2x. Okay? So these are individually functions of x and y. Okay? And here I'm saying that u, v, w are functions of x, y, and z. So can you give me an example? Just give me three functions of x, y, and z.
4u plus 2v.
What did you say?
Wait,
What?
can it just be like that? Like 4u plus 2v?
No, u has to be a function of x, y, and z.
Oh.
Yeah.
Just use x, y, z
Oh,
variables.
so
Yeah,
like
yeah,
2x plus 4z.
Okay, for v, what would I use?
3x squared plus the square root of 4z.
Whoa!
I want to challenge him.
Yeah.
Yeah.
Or 4zy.
4z, oh, okay.
What else?
Y.
X plus y plus z. Okay. So creative.
I'll
right?
take it easy on this one.
Okay. So that's an example. Okay, that's an example of a vector field. I plug in three numbers, it gives me three vectors, three numbers, which gives you a three-dimensional vector. All right, so these are vector fields. What do we do with them? Well, this is calculus class after all, so we want to differentiate it and integrate it. So that's what we're going to study for a few hours now. Okay. How to differentiate, how to integrate. That's what we're going to do. All right. So let's talk about differentiating first. Recall that nabla is round x, round y, round z. I mean, instead of writing round x, I just wrote this simpler notation. It's the same thing. So this is called nabla. Sometimes I wrote it down like round x, I, round y, j, round z. Okay, these are the standard unit vectors. When did we make use of this?
No.
Yeah, in the beginning, but when we were doing what?
Partials?
I mean, these are partial derivatives, right? When do we gradient? Yeah, when we defined gradient, instead of writing gradf, we said nabla of f. That means the gradient, right? Because if I have nabla applied to f, this is like this applied to f, this applied to f, this applied to f. This is what it means to apply this to f, right? And I mean, that's exactly what a gradient is. What's a gradient? It's just take all the partials, possible partials, f with respect to x, f with respect to y, f with respect to z, write it as a vector. That's called a gradient. Okay? And if you think about it, this is how we differentiated a multivariable function. Here, f was a function of x, y, and z, and we decided to differentiate it in this format. And it had lots of geometrical information there, and it was very useful for us to use it. Okay? So that's how we dealt with multivariable functions. Now, a vector field is a multivariable function, but it's not a single function. It's like three functions or two functions, depending on the dimension. Okay? So vector fields are also multivariable functions whose output is a vector rather than a scalar. And therefore, we have to make use of something like this. Now, the most primitive one that you can do is you can simply apply the nabla to the f. However, we will not make use of this one. Okay? Because in fluid dynamics, everything is just vector fields. Sometimes you even do this one. But this is used less often than the two other types of derivatives that I'm going to introduce later. Okay? But just to give you a slight idea of what this means, it's since f is three functions, you can differentiate u by x, u by y, and u by z. And you can differentiate v by x, v by y, v by z, and w by x, and w by y, and w by z. And that becomes an entire 3 by 3 matrix. So that's what you call something like a gradient of a vector field. But we will never use this one. So it's just a passing remark. Okay. Now, what's more important is the following. What's more important is the following. See, nabla is an operator because it operates on functions. If something takes a function and produces another kind of function, you call it an operator. But it's a vector valued operator, so it's like a vector. Vector fields are also vectors, and if you have two vectors, you know that we can do the following operations between vectors. We can do a dot product, and we can do a cross product. Right? So those are what we call divergence and curl of a function f. So divergence of f and curl of f. These are the two derivatives that we're going to use mainly. And divergence is defined as nabla dot of f. And let's see what that means. That means if I have u, v, w, no, if I have the nabla, which is round x, round y, round z, if I dot it with u, v, w, what's that? You do pairwise multiplication. So when round x hits u, that's ux. When round y hits v, it's vy. When round z hits w, it's wz. And then you add them up. Just like how you do dot products. Okay? What's the curl? Curl is I, j, k. Oh, no, sorry. I have to define it first. What's the curl? Curl is nabla cross f. So if you do the cross product between this nabla operator with the function vector field f, that's called the curl. And how do you calculate curl? You simply do I, j, k, place those elements of the vector, and place the elements of the vector u, v, w, and you just compute it, and that gives you the curl. Now there are physical meanings about what divergence of f is, what curl of f is, but that can only be explained after we do something called line integral. So at this point, I'm just going to give you some examples of computing divergence and curl, and afterwards, later, much later, I'll try to give you some meaning behind these things. Okay. Now, I only did divergence and curl for 3 by 3. If you go to 2 dimensions, divergence of, say, uv is like ux vy. Okay, you differentiate u by x and v by y, you add them up. That's called divergence. And curl of 2 vectors uv is simply you do round x, round y, u, and v. So it's like this part. So we can't do round z and w because it's a 2 by 2 matrix. A 2 by 2. In this case, it's a 2-dimensional vector, so you only have u and v and x and y. So in this case, you can only calculate this. And usually, this is not called the curl. If people say curl, it means this one with being 3-dimensional. But I will just call this as curl because this actually comes from this one.